about the homework number 2? Okay. I think this thing is on. This thing's on, right? Yep, okay. All right, so what do we have for questions?
Pretty much all of 2.2. 2.1.
All of 2.2, okay?
I mean, A, B, and C.
So which one do you want to look at?
Just start with A.
Start with A? Okay. And so this is we're given a bunch of information about a material and we have to determine how much it's going to elongate, right?
Yep.
So remember that the base form for these problems looks like this. Okay? What I recommend that you do for these problems is always set it up like this and then figure out which of these items do I need to determine. Okay? Use algebra to get it on its own. So if you need to determine the force that's being applied, rewrite it as such. Then go in and plug in your numbers and chug through the math. Okay? Because what can happen is if you start plugging in numbers and then go to start arranging things and you get lost in what you should be doing with what, you may not remember where your source equation is coming from. Okay? So that's what I recommend. But let's look at, so if we start back here, what information do we have for 2.2a?
1 inch square steel bar.
Okay. What else do we know?
2 feet long.
We know that it's 2 foot long. What else do we know?
They're asking what force needs to apply to an elongated 0.016 of an inch.
So our change in length is, sorry, Hunter, say it again, 0.016?
Yeah, inches.
So force applied equals something. What else do we need to know?
The modulus of elasticity.
Modulus elasticity of steel, right? But we can look that up on,
Well, it's given in the book right here. 29 million, isn't it?
yep. What page is it on?
55.
$29 million PSI. Okay? So that worked out nicely, right? In that we did that as our first example rearrangement. Okay, so this is how we would rewrite everything if we want to calculate our force. Okay, so we need that the force applied is going to equal the elongation multiplied by the area in square inches multiplied by the modulus of elasticity, all divided by the initial length. Okay? So if we plug that in, P equals 0.016 inches times, what's our area?
24 inches. Times.
What's our area?
1 inch square.
1 square inch, right? Because we've got a square steel bar that's 1 inch on a side, right? Our modulus is 29 million PSI. What's our initial length? 24 inches. Does everybody see why Zach made that change in dimensions from feet to inches?
Yeah.
Then he's got agreement in all his units, right? So these inches cancel. Our square inches cancel. We're left with pounds. If I describe to you a force in pounds, does that make you fairly happy? Should, right? Okay. So now you just have to chug through everything. So 29 million times 0.016 divided by 24. $19,333. Okay.
So I had 19.33 kips. Would you accept that?
That would be fine.
Okay.
Yep. Yep. If you didn't hear that, the question was, is it acceptable to use 19.33 kips? And yes, it would be, right? Because remember that 1 kip equals 1,000 pounds. So if we take this 19,333 divided by 1,000, that gives us 19.33 for the kips. Okay, good question. Yep, that's absolutely acceptable to do. So, summarize physically what we're saying, okay? If we take a 2-foot piece of steel, it's 1 inches on each side. Yes, sir.
Can you get a minute? Can you explain to us how you rearrange the equation? I think that's,
Okay, yep. Let's wrap this up and then we'll head back to that. So, 2-foot length, a 1-inch square steel, okay? We apply 19,333 pounds to that. Well, if we compress it, it's going to shrink 0.016 inches. If we put it in tension, it's going to expand 0.016 inches, okay? That's what it's telling us. Now, why is this important? I don't know. Maybe we have a little section where there's 2 columns in our building that they're 2 foot apart, and we need to put some sort of link so that we can put in a web stiffener of some sort, right? There's any number of situations where we can come up with where we might need to use this, okay? So does everybody feel comfortable, and we'll touch back on how we got to here, but does everybody feel comfortable with once we're here and we plug through everything, what went on with the math? Okay. So again, we'll start back with our base equation. So delta L equals PL over EA. So is the question, Matt, how do we start with this equation, or how do we maneuver everything around?
how do we maneuver everything around?
How do we maneuver everything around? Okay, so for this particular one, we were asked to determine the force. Okay, so maybe it'll help to say, let's see. So P equals force applied, L equals length, E equals modulus of elasticity, A equals area. Delta L elongation, although it's really just change in length. We could compress them as well. Okay, so for this particular one, we need to figure out what the force applied is. Okay, so we're just going to use algebra to move our terms around to isolate P. Okay? So if I instead told you, that's not a real good example. What if I said, x equals 3 plus x? What would you do to figure it out?
Minus x.
Minus x from both sides, right? Yeah, that's a bad example. Because now we're saying that 0 equals 3. We want to make it 3 minus x, right? Because then we'd add x to both sides. Okay, so 2x equals 3. X equals 3 over 2, right? Okay? What we're doing instead is we're moving things around with division and addition. So if I instead said x equals 4 over x, what would you do? Multiply both sides by x, right? X squared equals 4, so x equals 2. Okay? So for this problem, where we want to get rid of p, how would you get rid of e? Multiply both sides by e, right? So we're going to multiply by, let's move this over a little bit so we don't. So we're going to multiply by e. How do you want to get rid of a?
Same concept.
Same idea, right? Multiply by a. And then how do we get rid of L? Divide both sides by L, right? Everybody come along? Good? Oops, yeah, sorry, should. Right, we can cross off our L term. So force applied equals the area times the modulus elasticity times the change in length divided by the initial length. Okay? Do you want to look at another one of these, or do you feel comfortable doing these from here?
Maybe one more.
Do one more? Okay. Which one do you want to look at, Zach?
Are we staying at 2.2? I mean, B?
It's up to you.
Yeah, B.
2.2b? Okay. So, what's going on with 2.2b? What's the problem?
How much will a nominal 8 by 8 inch, actually 109.5 millimeter Douglas fir post, 12 feet long, which is 3.658 meters long, shortened under an axial load of 45 kips?
4.5 kips?
45 kips.
45 kips?
Or it could be.
So, we're taking a structural post, nominally 8 inches on each side. What is it telling you when it's telling you that it's nominally?
It's not the actual measurement.
Yeah, when we put a tape measure on that thing, it's not actually going to be 8 inches, right? Okay? Yeah. 12-foot length. Okay? We're going to apply 45 kips, 45,000 pounds to it. We have to figure out how much is this thing going to shorten. Okay? So, what do we need to determine?
Change in length.
We need to determine the change in length, right? So we don't need to do any manipulation of the equation ahead of time. We can just slap everything in right here and figure it out. Okay? Okay, so what's your force applied? 45 kips, right? What's your initial length? 12 feet? What's your cross-sectional area? Careful. What happens if we slap a tape measure on this thing? It's not going to be 8 inches on a side, right? So we've got to go to Appendix 8.8 for our structural timber.
Could you
Okay.
choose the millimeter number that they give you?
What do they give you in millimeters?
190.5. So it's actually
190.5, 8 and 25 is 200. Yeah.
You know what page that table's on? I couldn't find it in my book.
Is it 560 something? 660. 660? Hunter, give me 1 second. I'll be honest, I'm not a great dimensional timber mind off the top of my head. 8 inches though, if we convert that to millimeters, would be 203 point something millimeters. So that's probably an actual dimension.
Yeah, it says actually.
Oh, it does say actual dimension? Okay. So yeah, you could use that and convert it to inches. Yep. Yep. 7.5 by 7.5? Okay. So 8.8 starts on page 659. So our actual area is 7.5 inches squared. What's our modulus of elasticity for lumber?
16,000 KSI. But
16,000 KSI?
I got 1,790,000.
Is that what they have in the table?
well, I think it's 16 million.
60 million PSI. Yep, yep.
So in the book, it's on a range.
What page are you on?
We were on like 56, right? I didn't get there.
Table must be on another page.
Yeah, we weren't able to find the table. I use this for wood, depending on the species, from 1 million to.
Well, we've got that table that gives us the value, right?
I think it's 1.6.
I got 1.79 million. I looked it up online and went through a table.
If you look at.
Oh no, it's 1600 KSI. I have a zero crossed
Look at
out.
page 49 at the bottom, elasticity for Douglas fir.
Yeah, it's 1.6 million.
Page 40.
Yep, yeah, if you go to page 49 in chapter 2, it has table 2.1, selected values for common structural materials. So you got structural steel, you have concrete, and then at the bottom we've got structural lumber. Okay, so our Douglas fir, used for select structural grade posts and timbers. So yeah, our modulus elasticity, 1.6 million or 1600 KSI, right? That's fine, we made it there. What page did I say that was, 49?
Yeah.
Okay. Okay, so because we changed to KSI, that's going to work out in our favor here, right? Because the kips go away. We have square inches here, so those go away. What are we left for with units? We're left in feet, right? Which if we're describing a change in length, if I describe something to you in a change of length in feet, do you feel pretty comfortable with that number coming to you? I feel pretty good about that, right? I can envision a change in length in feet, right? Okay, so from here you just need to plug and chug. What does it end up coming out to be? Remember to square your 7.5, right? Because it's 7.5 inches on a side.
.006.
0.006 feet, okay? What might you want to do? Now, if you report 0.006 feet to me, that's absolutely fine, that's a correct number. What might be more useful to us?
Inches.
If we multiply it by 12 and convert it to inches, right? So it becomes 0.072. Okay? Now, I don't know if that provides us much value. I think I have as equally difficult time envisioning 0.072 inches as I do 0.006 feet, right? But we're talking a fairly small number, okay? Is how much this thing is shortening. Okay, but either of these values would be acceptable. Any questions on these items? How we arrived at them? Good? Okay. So, how much more time do you need on these? Can you have them done tonight, tomorrow night, end of the weekend, before class, next time?
Probably say minimum, for myself, tomorrow night, I work tonight, so.
Tomorrow night?
Class all day tonight.
Tomorrow night reasonable for everybody?
Yeah.
Okay. So I will update that. Ugh. What does that make it? 2.7? Okay. For the online class, which doesn't affect those of you that are here, I'll give you until next Tuesday, okay? So that they have time to look at it with their work schedules. Other questions on homework number 2? Hearing none. In the past, when I've taught this class, at this point we've pivoted and we've stayed with axial forces and we've looked at truss analysis. And there's 2 ways that you can analyze trusses, and one of the ways that you can look at them is by a system called method of joints. The other is called the method of sections. And the idea behind it is that if you use the method of joints, you blow up the truss and do analysis at each of the joints. Give me a second here, I'm just going to track down. So if we were going to do method of joints, what we do is we take each of the member joints of this thing, blow it up, and conduct analysis around the joints. Method of sections, we make cuts through the different sections of the truss and perform analysis on the cut sections, okay? We're going to bypass method of joints, method of sections. It bogs us down. We end up spending like 3 weeks on it, and I think that there's more valuable time that we can put in on other concepts. So we won't start applying it at this point. We'll bring trusses back later on. It'll be your final project. We'll be actually constructing and testing a truss. And what we'll look at is, rather than trying to determine and predict strengths within each of the members, what I'll have you do is we'll assign you cost values for all the materials. Okay, so the staking posts that you use, the plywood gusset plates, and the wood glue. So you'll have a cost value for all of them. You'll have a cost value for your time in designing your truss. You'll have a cost value time in constructing your truss. And so how you'll be graded on the final project is, what's your ratio of strength of your truss to cost, okay? Because that's ultimately how we get assessed in the real world, right? The stronger the bridge that we can build for the cheaper the price, the better off that we're gonna do. Because I mean, we can make a bridge that is stronger than anything else on earth, right? What's the problem with that? There isn't a taxpayer alive that's gonna pay for it, right? They're not interested in paying for the strongest bridge possible. They're interested in paying for the weakest bridge possible that they can use, right? It sounds bad to say, but that's what we're interested in doing. What's the weakest possible bridge that we can build that meets the requirements of whatever it is that's traveling over this thing? Train traffic, car traffic, truck traffic, okay? So that'll be the final project. We'll come back to this a little bit later on. So the next thing that we'll talk about, we'll skip the rest of chapter 2 in axial forces, and we'll actually move on and start talking about shear forces. Okay? So, chapter 2, talking about axial forces. So we're considering taking some sort of material and applying a load axially, okay? In chapter 3, when we start talking about shear, just gonna make sure I don't tear something that I need. The process of shear is that you have resistance to a force and you have that force applied, okay? And if we overcome the resistance of the material, we end up shearing it, right? So if you think about a steel beam, a concrete beam, we get a nice, well, not necessarily always nice, right? But a straight-ish fracture through the material itself when we see shear. And what's happening is, if we have a concrete beam here, and say that we have, I don't know, we have some sort of concrete column over here as well, right? This is a force applied by the building, say building weight. And the column is providing resistance, okay? If we don't size this thing appropriately, what could happen is we could end up getting a break in that concrete column, where then the thing ends up fracturing, okay, and shearing off. Make sense conceptually what we're talking about? Okay. So, forgot to print my little cheat sheet. Just like when we worked in the axial forces and talked about direct axial forces, the first concept that we talk about is direct shear force. Okay, and so we won't go into great detail. We'll talk for probably about the next maybe 10, 15 minutes and do a couple examples. So direct shear force we can think of, I think the easiest thing for you to probably envision say we have a couple steel members that we're joining, okay? And in this case, we're bolting them together, Okay, now we're only in 2 dimensions. So you have to envision that on the back side of the board over in green 39, there's another plate where the bolts are held into place with nuts. Okay, so everything's secured. The idea is, as this building is loaded and snow deposits on the roof and the wind blows on the side of the building, these 2 beams are trying to pull apart, okay? And so this plate is set into place to keep it together. And maybe we also have a column that's in between them. A fairly slender column, it looks like, due to the depth of the beams, but it will work for our intents and purposes, okay? So we need to make sure that the bolts we select have sufficient shear resistance so that when these 2 beams try and pull apart, if we flip this thing over, and so we have our steel beam, we have our steel plate, and we have our bolt, right? So if we give these items depth, so as our steel beam tries to pull away, and the steel plate tries to hold in place, we don't actually shear that bolt off, okay? Does that make sense conceptually to everybody, what we're looking at when we talk about direct shear stress? Okay. So how we determine it, it's the exact same methodology that you used for the direct axial stress. Okay, so we say that well, no, because we use V for shear stress. We call that our load, right? And A is our area. Okay? So coming back to this section, let's envision that we have, it's a load of 5,000 pounds that's exerted on that steel beam. Okay? Well, if we instead of trying to figure out, well, how much is on each bolt, let's just figure out with 1 3/4 inch diameter bolt and forget the fact of the buildup for the thread, everything like that, okay? The bearing area of the bolt itself will be the bearing diameter of the bolt will be 3/4 of an inch, okay? So how would you go about determining what's the direct shear stress on that bolt? 5,000 pounds. It's a circular bolt, we'll say. We're not using anything weird like a square bolt or a trapezoidal bolt or something like that. Something that we know how to use.
The area of a circle.
Area of a circle, right? What's area of a circle? What's the radius of our bolt? 3/8 of an inch. Okay? Everybody still along for the ride to this point? Questions at how we got there? No? Okay. So then from here it's just plug and chug, right? Go for it.
223.81 PSI.
223.81.
I got 11,000.
Yeah, I was gonna say, I was thinking about 12,000.
11,317, 168.
Okay, so did you remember to square the 3/8? Seems, I think that's probably the most likely source, Matt. Because you're off by a factor of about 50.
Okay.
Okay. Okay. So 11,317 PSI. So what that's saying is, if we know that 5,000 pounds is the maximum load that's going to be applied, and we only wanted to use 1 3/4 inch bolt, it would need to have a capacity of 11,317 PSI.
Do we want to round that up to 318?
Sure. Because what did it end up being, 0.6? Yeah. 318 would be fine. Now, full disclosure, when I'm grading your homework, if you got 11,317 or 11,318 for this class, I'm not going to mark you off on that, okay? The reason being, if we just drop one bolt in here, and we're envisioning our capacity to be 11,318, what's wrong about our assumption if we know that 5,000 pounds is going to be continuously applied here?